right, so let's diagram inhalation here, right? Out in the atmosphere is the pressure of the atmosphere, which we said that we always want to assume is zero, right? So we've got PATM outside of this person. Here in this person's little alveoli, we have P pull, or the intrapulmonary pressure. And then over here, right here between the two pleural membranes, I have P-IP, which is the pressure in the intrapleural space. When you inhale, the external intercostal muscles all contract. And what they do is they bring the ribs closer together. And they move your thoracic cage both upward and outward. At the same time, the diaphragm is moving downward. So we're going from a chest cavity that looks like this to a chest cavity that kind of more looks like that. Okay, so as this outward force is happening and the ribs are moving up and out, for a very split second, the intrapleural space expands because it's kind of the parietal membrane is attached to the connective covering of the ribs. So the ribs move the parietal pleura outward and the intrapleural space expands, right? And it increases in volume. And so the intrapleural space decreases in pressure as we inhale. And almost immediately, the visceral pleura is like, whoa, whoa, whoa. If you're going to move outward, I'm going to have to move outward with you. And what the visceral pleura does is it starts to move outward, closing that intrapleural space. Well, that visceral pleura, don't forget, it dips into the lobes of the lung and forms that connective tissue. So as the visceral pleura moves outward, it also expands all the alveoli. So everything, your chest cavity, all the way down to the little tiny alveoli, are all expanding. And what happens is that inside the lungs, the volume is increasing. And we know that by Boyle's law, that means that the pressure should be decreasing. And yes, it does. In fact, the pressure in the lung, P-pole, is going to decrease so much that it is actually below the pressure of the atmosphere. And what we've done here is we've created a gradient. We've created a situation where the pressure in the atmosphere is high, the pressure in the lungs is low, and air can flow down that gradient. At first glance, inhalation appears to be quite simply following the law of Boyle's law. By increasing the volume in the lungs, we create a pressure gradient down which air can flow. There are a few things that can affect that process of inhalation. As with our patient in the case study who has exercise-induced asthma, bronchoconstriction and mucus production in the conducting respiratory system can limit the volume of air that gets to the lungs, and it can limit how quickly that volume gets there. As in our patient in the case study, our patient's young, our patient's healthy, they're an athlete. There's nothing wrong with their lungs. Their problem is truly what is called a restrictive disease. And those are diseases having to do with the delivery of air to the lungs, not the capacity of the lungs. There are other diseases that are known as obstructive diseases. And these are diseases that struggle with the pressure of inhalation, struggle with the volume of the lung. For example, COPD, chronic obstructive pulmonary disease, has to do with inhaling and exhaling unequal amounts of air. Okay, so a patient with COPD takes a breath and then they don't exhale the same volume of air that they inhaled. And so the next breath that they take doesn't have the right volume of air that's needed for external or alveolar respiration. And what this does, this small breath that happens, it triggers responses by the respiratory system, such as coughing and trying to deeply inhale or inhale at a faster rate. And these responses, they're triggered mostly by the lack of oxygen. So the deprivation of oxygen in COPD actually drives them to correct their breathing on subsequent breaths. The next little tidbit I seriously only know from watching ER in the 90s, probably. But I guess you don't ever give patients with COPD a nebulizer. A nebulizer takes away their low oxygen triggering and effectively takes away their ability to correct the COPD. Another concept that greatly influences your ability to change the volume of your lungs during inhalation is a concept called compliance. Compliance is a two-pronged subject. It's concerned with the stretchability of your lungs during inhalation, but it's also concerned with the recoil of your lungs during exhalation. Stretchability and recoil together are known as distensibility. I put this picture here of somebody blowing up a bubble out of bubble gum, and I thought originally that they were blowing up a balloon. I left the picture. Have you ever tried to blow up those cheap balloons from the dollar store? I'm sorry, because I have. They're like rubber erasers, right? They're like thick and unbendable. And you go to blow one up and your ears pop because it takes so much force to push air into it. So now, at the end of the day, it's been inflated all day in the hot sun at some family picnic or child's birthday, and you pop it to deflate it and throw it away because you know how bad those balloons are for wildlife. And when you pop it, it barely changes shape. Now, all that's stretched, it's all stretched and it won't go back to its original shape. Both of these situations describe compliance. In both analogies, the balloon has low compliance, both blowing it up and popping it. So let's go over some of the things that influence compliance in inhalation and inhalation only, because the rules are different for exhalation. In inhalation, you want stretch, and you want that stretch to be easily achieved by your diaphragm and external intercostal muscles. In order to achieve high compliance in inhalation, the thoracic cage has to be able to move outward. The external intercostal muscles, those are the muscles between each of your ribs. And when they contract, they move your thoracic cage outward and kind of a little bit upward. So arthritis in the rib cage can curtail this movement of your thoracic cavity. This would effectively limit your ability to inhale the correct volume of air, which then affects your ability to create a pressure difference. So therefore, somebody with arthritis of the rib cage would have low compliance for inhalation. Another thing that affects compliance in inhalation is a topic called alveolar surface tension. And this concept involves the stickiness or cohesion of water molecules on opposite sides of an alveolus. They want to stick or cohere to each other and produce surface tension, which is not good for inhalation. You have to overcome alveolar surface tension with every breath you inhale. Alveolar surface tension refers to the fact that your respiratory membrane is watery. And there are water molecules on this side of the alveolus that are strongly attracted to water molecules on the other side of the alveolus. Water molecules like to cohere to each other and form hydrogen bonds. They like to make surface tension with their cohesion. And surface tension of water molecules prevents alveoli from expanding. More effort by accessory respiratory muscles is going to be needed to overcome the surface tension of the water molecules and inflate the alveoli. This is where those type 2 pneumocytes or great alveolar cells come into play. These cells secrete a substance called surfactant. Surfactant is like a detergent. It's both polar and non-polar at the same time. So it can get out grass stains and oil stains. Surfactant, you can see it in this picture. It's just a very light blue that's highlighting the lining of our alveolus here. And it's breaking up that alveolar surface tension, making it easier for the alveoli to expand. But what if you don't make surfactant? That's the case in premature babies. Surfactant isn't made until about 2 weeks prior to birth. Why would you need it? Right? It's not like you're going to be using your lungs. So premature babies may not be able to provide enough force to increase the volume of their chests and overcome the surface tension that's holding their alveoli closed. And this is why premature babies will often be put on a vent. Ventilators essentially blow air into your alveoli, forcing them open. And then, of course, to exhale, there are elastic forces and the alveolar surface tension. Alveolar surface tension seems to be a negative thing when we're talking about inhalation. Correct. That's because it's a force that you have to overcome to inhale. However, alveolar surface tension is really important in encouraging exhalation. It's one of the forces that encourages your alveoli to collapse passively without your effort during exhalation. So I think it's a love-hate relationship with alveolar surface tension, right? Here you want just the right amount, but not too much. Aren't there fairy tales about that?